All right, there we go. All right, so picking back up where we left off the other day. I think we should be at the bottom of page 1, right? All right, let's step back a little bit and just real quick look what we got so far, just to remember. So in one of these we had remaining at rest. This is for a position time graph. There's always going to be a flat line like that, okay? If we have something moving steady, it's always going to be linear. Linear is a fancy name for what? Straight. So if you had two linear lines, the steeper one, like B here, is moving faster than A, right? If you could have one linear one upward and one down. This one's a positive slope. The one looks like it's going uphill. So that represents something moving constant velocity in the positive direction. This is constant in the negative direction. Then let's jump down to these ones where we ended yesterday. If there's a curve, that means what might be going on? Some sort of what? Yeah. Acceleration, either speeding up or slowing down. If the curve gets steeper like this one does as it moves along, then we get faster. If the curve flattens off, then we get slower. And it could happen in different directions. This one's getting faster because it's steeper. This one's getting slower because it's flattening off. Basically, the next 4 questions on here. Go full screen on this so you can see it better. It's really just like these situations up here. They're just asking it in a different way. If you happen to recall from like a week or so ago, we learned that just saying the direction of accelerate or the sign of acceleration doesn't really tell me if we're speeding up or slowing down. We also have to know which way we're going. And we said it's an easy pattern if you remember it. If you are going in with a positive V and a positive A, you're speeding up. Plus plus speeding up. If the signs are the same, you're speeding up. If the signs are different, you're slowing down. So if we had a plus V and a negative A, slowing down. If we had a negative V and a negative A, same signs. So it's doing what? Same signs, what did I just say? Speeding up if they're the same signs. All right? So basically that meant just because you have a negative acceleration doesn't guarantee you're slowing down. You could be speeding up if you're also going negative in the first place. So just last time. Same signs, regardless of the signs. For those two values, means speeding up. It's another way to say speeding up. If they're opposite, you're slowing down, and we got to draw it that way. All right. So these are really similar to these above, but above it actually told us speeding up and slowing down. These ones aren't going to tell us. We have to infer that, and then they're really going to be ones just like graphs, just like this. So with that in mind, let's finish off a few of these. Okay. So this one says plus plus, right? Plus velocity plus acceleration. Now we also need to know which way we point does it point up or point down to speed up? So what do you think? Up. It's all based on the velocity. If it's plus velocity, to get up more positive velocity, we got to sweep up. If that was a minus velocity, we go down. But either way, it's speeding up. So that means we need a curve that sweeps upward and gets steeper for that one. There's only one we draw on each of these. Does that make sense to everybody? Whenever we do anything like concept builder wise on this, you guys will have this available in front of you. So to use to help you. Because I know after you do so many of them, they can still be a little bit confusing. So I'll never have you like a quiz or anything graded on this that you can't have this in front of you, okay? To help you. All right, the next one says moving with a positive velocity and negative acceleration. If they're opposite signs, that's got to mean slowing down. But slowing down, if we're going with a positive velocity, that means we're going in the positive direction. Slowing down in the positive direction, we've got to go upward as well, but slowing down means it's got to flatten off. This one we got steeper, that's why it's speeding up. This one's flattening off, that's why it's slowing down. And we got 2 more variations of that on the top of the next page. Everybody good so far? All right, flip to the next one. Opposite signs, negative, positive, slowing down again, right? We got to slow down while going negative since that's the original direction on the velocity. So that would be like that. And then we got minus, minus. Got to be speeding up, right? Speeding up while going minus since that's the direction the velocity is in. So we got to get steeper going down like that. So they just, on those 4, they just didn't use the word speed and velocity. They implied it by the sign, or speeding up and slowing down. They didn't use those words. They implied it by giving us the signs. All right, the next little section is simply going to flip-flop what we've been doing. We've been giving a description how to make the graphs. Now we're going to give the graphs and have to make a description. But look at all four of these. These all have two segments. So we're going to number them in each one. Now there's not a lot of room to write in here even if you blow it up, so we're going to keep it as brief as possible. Okay? So let's call this segment 1, though, so we know which one I'm talking about. The dot on the graph represents a different segment of motion. We have to do each of them separate. So for segment 1, we'll explain it over here. It's linear, and how would we describe its slope, guys? Yeah. No, it would be curved if it was accelerating. So linear means it's going constant, right? What kind of slope is this? You guys, 3 choices: 0, positive, or negative. What kind of slope is that? Positive. It's over an uphill, right? So what we could say, even if we didn't see this thing in motion, if we were given the graph, we would know this represents for segment 1 an object that is going with a constant positive velocity. It's constant because it's linear and not curved. It's positive because it's uphill, right? So I'll abbreviate some of that to get in. Constant positive velocity. Now let's go with segment 2. What do we say if it flattened off completely? What does that mean? What does the object do? Yeah. It's at rest, exactly. That's as much as we need to put there. I'll get there. Now this one, both of them, if we related it back to the other one, let's do one segment at a time again. We'll call that one segment 1, the other one segment 2. But both segments in this one to the right, both of these would have constant positive velocity, right? But we could compare them. Which one's going faster, segment 1 or segment 2? 2, because it's steeper, like we learned, right? Very good. So we could say both of them are similar in the fact that segment 1 is also constant because it's linear, positive velocity. But since we have another one like that to compare it to, we could just put slow by it. It's slower because it's not as steep. So we're just going to write beside segment 2. This is also constant because it's linear. It's also positive because it's sloped upward. Velocity. But it's faster, right? Because it's steeper. As long as we could identify those, that's good. Go on to the bottom here. All right, segment 1 on the bottom. This one does have a curve. So what's it doing? Yeah, accelerating. Now, is it speeding up or slowing down? Is it getting steeper or flatter? As the curve goes along, is the curve steepening or flattening off? It looks like it's getting steeper, so that means it's speeding up. So segment 1 is speeding up, and it's going to the positive direction, right? Sweeping upward. So this would be something that is speeding up in the positive direction. Let's abbreviate all that. Speeding up, positive direction. But then, segment 2, we don't have a curve anymore, do we? So we're back to some of the earlier ones. Constant positive velocity, right? So this might be something like that happens like a very simple, realistic thing. When you're like at a stoplight, you have to accelerate, right? You accelerate up to a certain speed. You don't accelerate forever, at least I hope not, right? You accelerate up to probably at or near the speed limit. Nobody goes over the speed limit, right? Yeah, and then you probably stay at that speed until something happens, like a turn or you have to hit the brakes, right? So this could be an example of somebody speeding up to a certain speed, but not too much because they want to stay there then and stay steady. The linearness of the part 2 means they now stay at a positive constant velocity, or a constant positive velocity, however you want to say it. Constant positive velocity. How about segment 1 of this one, another curve? So this curve is a little different. The last curve represented speeding up. This one represents what? Slowing down. And we can tell that because it doesn't get steeper, it flattens off, right? So in segment 1, we're slowing down, but it is going upward while it's slowing down, right? So it's slowing down, but still going in the positive direction. And actually, it slows down so much that it becomes flat. So segment 2, flat meant what again? At rest. So it slowed down so much it it completely remains at rest now. Complains at rest now. Does that all make sense to everybody? Okay. Okay, now putting some numbers to it. So we learned by the general shapes. We're only going to ever do slope on linear ones because we really can't take slope of curved ones. We can, but at best it's an average. We usually apply slope, like think back to like algebra and stuff. Slope you use linear lines for, right? And now we know the slope of these linear lines on position time graphs represent the velocity. So in the earlier graphs, there were no numbers on them, right? We were just looking at the trends of the shapes of the graphs. Now, if we have numbers on them, we could actually find the real velocity using a formula which we already used, but this explains where it really came from. Remember back probably close to 2 weeks ago, we learned the formula V equals d over t. Velocity equals displacement over time, right? And I told you someday we're going to learn where that came from. It didn't come out of thin air. So before we actually complete these ones, and you could show work on a separate page like I'm going to do it because there's not much room in this one. You could add another page if you want. But before we do that, let's think about how we did slope probably way back in middle school for the first time, or 8th, 9th grade, maybe even before that, okay? How many points do you need to find the slope of a line, the minimum amount? How many points do you have to know on a line to find slope? Yeah. 3, you could have that many, but the minimum amount you need is just 2, right? It doesn't even have to be start and finish. It has to be anywhere on it, okay? So usually if you remember back, let me zoom in on the first one here. We try to find nice points so we don't have to estimate numbers. This isn't exactly graph paper, but it's kind of set up like it, right? If you recall doing it on graph paper somewhere in your life, I'm sure you did when you first learned about this, you always try to find 2 nice points that are on corners of boxes. Because corners of boxes were nice numbers. You didn't have to estimate, right? There was no fractions involved if you could do that. So let's try to do that. Sometimes the beginning end points are the nice points. So this beginning point's a nice point. It starts right from the origin, right? So I'm going to put a dot right there. It looks like the end point line ends on a nice point, doesn't it? So let's use the beginning and end. And to find slope, we've got to know the coordinates. Well, the origin is 0.00, right? What's the coordinate of this point? Remember, the x always comes first, then the y. X, comma, y. Where am I horizontally on here? Yeah. Good. 520. We all okay with how we got that? All right. Now, I'll do it the generic math way, but we just need to realize what it really represents. Now, in generic math, you would have called this point x1, y1. Right? Does that ring a bell? And this point would be x2, y2. And it is because this one's on the x-axis, this one's on the y-axis, but we're better than generic math right now. We're naming our axes. So technically the y's are positions, aren't they? And the x's are times, aren't they? So when we actually do the calculation, yes, slope is y2 minus y1. This looks familiar, right? Over x2 minus x1. But technically, if you think about it, y2 minus y1 is a change in position. Because that's what the y-axis is, position, right? And guess what we defined changes position as like a week or so ago? Displacement, right? So when we do 20 minus 0, because y2 was 20, right? y1 was 0. And on the bottom, the x's are actually times, right? That's what's on the bottom of that equation. 5 minus 0. So doing the slope formula is actually really using v equals d over t. Just more specific. This is the slope formula for this kind of graph, and that's simply 20 over 5, and that's obviously how much? 4. And this represents a velocity. Since my position was in meters and my time was in seconds, this is 4 meters per second. Make sense? So there's the work. I'll just transfer that answer on the page. So V equals 4 meters per second. It came out positive. We don't have to stress the positive, but you can if you want. If it's obviously not negative, it's positive, right? A little check you want to do, because just in case you made a little calculation error. Look at the graph itself. We've already learned that if it goes uphill like this, it has to be a positive slope, right? So this doesn't guarantee you're right, but it could guarantee you're wrong if you made a silly mistake. If I got a negative value out here, I have to be wrong, right? Because I clearly can see this is a positive slope. This is a positive velocity. So that thing is traveling, if we actually have numbers on the graph, which in like lab situations we will, at 4 meters per second. Now I expect you know how to take slope by hand this way. When we do labs that graph stuff for us, one nice feature is that saves you some time. You can find the slope by the click of a button, you'll see, when we do our first one. And you basically just hit what is the slope, and it'll calculate it for you. But you should really know what it's doing and why, and that's why. Okay? All right, so here's what I want you guys to do. On your own, but we'll come back together and check it in a few minutes here. Finish the rest of the boxes. Show your work on a separate page so it's not all jammed in there. Just put the final answer. You can mark your dots on this page that you used, like I did. But and you can even mark the points. But put your work on a separate page, and somewhere in the bottom, put what your final answer is, V equals. All right, find 2 nice points to do. Be very careful with your numbers and you pick the points right. And in like 5 minutes or so, whenever it seems like you guys are done, we'll come back together and we'll check our answers, okay? Just for a second, I'm going to finish off the work too, and we'll just check it together. Looks like on the fourth one, guys, to find a second point, it doesn't look like it hits anywhere real nice, does it? So estimate the best you can wherever you hit the second point. As long as you're close to my answer, that's fine. I'm still going to use the end point, which to me looks like, kind of hard to tell. Maybe use a regular piece of paper or something. It's not full grid paper up in here. It goes by 2, so 2, 4, 6, 8, 10. Looks to me it's around 6. I'm going to estimate vertically on that one. Actually, let's estimate it to 5. It'll make the numbers work out nicer, okay? Everybody see what I'm talking about? It's like halfway almost. Estimated for that. You went to 4, that's fine. You won't get the exact same answer than me, but I'll be lenient there because they don't have full graph over there. It's hard to really tell. I'm going to use a 5 and the numbers look that way. Yeah, they do. And I see what they're going for there, but it doesn't look nice, right? All the other ones worked out nicely. I'll be back up in a second. Up in the beginning here. So just doing the same thing I did. I'm going to work on a different page. I'll flip through in a second. So let's go to the one to the right. Actually, even though it's not the same exact starting point and everything, you could even see when you compare it to this one and this one, doesn't the line and slopes look like parallel? Right? If they are, we don't want to eyeball it, but when we figure it out, we get the same answer for this one. It started at a different position, but it still had the same slope, which means it's going the same speed. So this point was 0.5, that was 5.25. So when we do the work, we do in green for that one, it's 25 minus 5 over 5 minus 0 when we do y2 minus y1 over x2 minus x1. You get positive 4 again on that one. Let's go down to the bottom left. Now, what do we notice about the bottom two? Even before I run the calculation, I should be getting out what kind of numbers? True, they were close to the same because they were close, but more about, look at the way they're pointing. What kind of slopes do they both have? Because they're going downward. What should I expect when I calculate? I should get out what kind of numbers? Negative, because they're both going down, right? And I do. So if I use 0.25 for that point and 5.0 and run that formula, then I get about negative 5 meters per second. That one should have come out pretty nice. This is the one, though, where you might have estimated this last point differently, and it didn't hit any other nice points. So I estimated it as 5.5. But if you do that, it will come out nicely to negative 4 meters per second. If you estimated that to 6 or 4, it'll be a little bit further away from this. If I gave you one on a test or a quiz or something that was graded, I would make it look better than that. So, okay? I wasn't not set up that great. So main point is, if we actually calculate the v by taking the slope, that's what it represents, the velocity. And it's a velocity because velocity is a vector. The magnitude's the number, and the sign is the direction. Right? When we have 1D motion, we can only go positive. That's one way. Negative is the other way. Question? Oh, yeah, sure. So this would be the work for the rest of them. If you have any questions, just say something. That would be for the bottom left box there. Let's see what you did. Like I said, a lot of times when we use the software we use for some of these sensors in labs we do, it's going to just find this by a click of a button. But that's what it's really doing, is just immediately calculating this like we did right here. All right. So there's another second type of graph that we look at called velocity time graphs that relate similar things but are different from these. We're going to spend next week, at least early in the week, on those. So we're pretty much done with features of position time graphs. One question I want to ask, just because this study guide didn't. We had curves on it. We had linear lines. We talked about what those meant. I want to just throw out a question. You have to write this down. Just pay attention. Let's say I gave you a PT graph. Again, you didn't see the motion. I just gave you a graph of the motion. What if there was a full parabola, like something like this on it? What must that mean? Let's split. It's helpful to split this into half. Yeah. Well, they're on an arrow at the end. Could mean that. So let's in generic math we do that a lot. Let's say it doesn't. Okay. Let's keep the arrow off of it. Yeah, you're right. It would go that way forever. But let's just look at what I have drawn here. Well, let's split it into halves. You might remember this term for algebra. That first of all, that's a full parabola. Okay. You might remember that the midpoint or turning point of a parabola is called the vertex. Does that sound familiar? Okay. So let's take halves, because we already studied halves of it. That happened on the whole page. So let's just take this first half. It's coming and it's curving, so there's got to be acceleration, right? So for the first half of the trip, it's curving and it's getting less steep. If it gets less steep, is it speeding up or slowing down? Getting less steep from here to here. Slowing down. And then all of a sudden, it gets more steep. That means if it's starting the second half of it gets more steep, that means it's speeding up. So, and it went in the other direction, didn't it? So what this represents is turning around. If something fully turns around, like you guys will see this when we eventually get to that first lab. We have to get through VT graphs first. When we eventually get to that first lab, if you walk like this in front of it and turn around, you'll get a full parabola. As long as you speed up and slow down without like jerky motion, you'll get a full parabola. Because at that vertex, to turn around on a straight line axis, you have to do what for at least a moment? Stop, and that's the vertex. Even if you do it super quickly, go one way or another, for a moment you've got to stop, else you can't fully turn around, right? That brief moment is right there at the vertex. And we could see one shape this way as well. We could also see a possible vertex that way, anywhere on the graph. That's the same idea, but in this one, we're slowing down in the positive direction, then speeding up in the negative. This one, we're slowing down, going towards the negative, then speed up in the positive. It's the same idea. The main thing is a full parabola shows us the object turned around. It's the only other extra thing I wanted to include. So we are done like about 10 minutes early here. I want to use that 10 minutes to try to see if I could get our class started on this. If I do, I'll give you the information. But I just got all the login information myself. Tomorrow, since this is the first full week of school, every full week we have, we're going to do a How Stuff Works assignment. That's the thing where we read and write a summary. Usually we do it on Fridays, but I'm doing the first one on Thursday because I got to give you directions how to do it and exactly what I want done. Once you get the hang of it on a Friday, I'll come in and say, hey, How Stuff Work assignment's posted, get on it so you get it done. 18 minutes isn't much, but it's enough to get them done. Okay? So tomorrow I'll spend like 5 or 10 minutes telling you what you got to do, what I expect. The rest of the time to do it. They're easy points as long as you follow directions. And they're always about something we're talking about. I think I already mentioned to you, this one's going to be on how GPS works and general ideas behind that. And when you're done with it, we usually talk a little bit about it that day or the next day if we run out of time about like how it related to the class. So that's what we'll be doing tomorrow. So you guys could do whatever for the last 10 minutes while I try to figure out how we get on this thing. Probably this Friday. By then, I hope we're on this. We'll probably play around a little bit on the concept builders while we're logged in and see how it, because I don't know how it's going to track our progress. I've never been into the system logged in. We might just together play around on it a little bit